Pythagoras' theorem involved right-angled triangles. Side A here is opposite the right angle, the hypotenuse is A. Pythagoras' theorem was a squared equals b squared plus c squared. So if a triangle is right-angled, a squared equals b squared plus c squared. Here it is here. If the triangle is right-angled, then we can say a squared equals b squared plus c squared. The converse of Pythagoras' theorem works this backwards. It says, if it's the case that a squared equals b squared plus c squared, it must have been a right-angled triangle. So here, if you know the three sides a, b and c, and you can show a squared equals b squared plus c squared, you've shown that that angle there is 90 degrees. Hypotenuse A is opposite angle A. You've shown angle A is 90 degrees. So here's converse of Pythagoras' theorem. If a squared equals b squared plus c squared, then the triangle is right-angled, and it's right-angled at A. That is, the angle BAC is 90 degrees. So you're showing a triangle is right-angled by showing Pythagoras works on it. That's the converse of Pythagoras' theorem. So if we want to show whether or not a triangle is right-angled, you need to show that Pythagoras would work on it. Here we want to see if 6 squared plus 9 squared makes 11 squared. Now 6 squared plus 9 squared does not make 11 squared. Conclusion: 6 squared plus 9 squared is not equal to 11 squared. The triangle's not right-angled. Here the triangle's 5, 12, 13. Does 5 squared plus 12 squared equal 13 squared? 5 squared plus 12 squared does make 13 squared. So we can make the statement, since 5 squared plus 12 squared equals 13 squared, the triangle is right-angled. Now normally you have to set out better working than that. So when we are asked to show or prove a triangle is right-angled, we need to set the working out, and we need to state that we're using the converse of Pythagoras' theorem to show a triangle is right-angled. So in this example, the 5, 12, 13, you show the working to show 5 squared plus 12 squared is equal to 13 squared, and you make the statement, since 5 squared plus 12 squared equals 13 squared, by the converse of Pythagoras' theorem, the triangle is right-angled. So that's an important statement. There's no answer to this question. It's not asking you to calculate something. It's asking you to show or prove. So you've got to demonstrate with the working and with that statement that that triangle is right-angled. Now here's a harder example. Show the triangle ABC is right-angled. That's a red triangle. To show it's right-angled, you need to show that Pythagoras works on it. But you've got this side missing. You don't know AC. You need to know all three sides. However, the green triangle has a square in the corner showing it is right-angled. You can apply Pythagoras' theorem to the right-angled triangle. To work out the missing side AC, it's a shorter side. AC squared is 17 squared minus 8 squared. So this is Pythagoras' theorem on the green triangle. AC squared equals 17 squared minus 8 squared. 17 17s, 8 8s, follow it through. AC is the square root of 225. It's exactly 15. There it is there, AC is 15. We now know the three sides of the red triangle. We can show it's right-angled if we can show 9 squared plus 12 squared makes up the 15 squared. So this is the converse of Pythagoras' theorem we're now using. There's 9 squared plus 12 squared. There's 15 squared. They are the same. Since, labelling the sides ABC, since 9 squared, that's the AB squared, and the 12 squared, that's the BC squared, make up the AC squared, that's the 15. So that's 9 squared plus 12 squared makes 15 squared, just using the lettering. Since this is the case, by the converse of Pythagoras' theorem, the triangle is right-angled. So that's an application of Pythagoras first to a known right-angled triangle, and then the application of the converse to a triangle here, 9, 12, 15, to show or prove it's right-angled. This is part of a worksheet. You can download it using the link in the description. It will have the answers, or you can pause the video to do the questions. Simply show or check which of these triangles are right-angled and which aren't. Now you're checking whether 6 squared plus 8 squared makes 10 squared or not. There's the second half of that worksheet. So it's applying Pythagoras and then applying the converse to show a triangle's right angled. Now, the answers are 6 squared plus 8 squared did make 10 squared, so that is right angled. Yes, it's right angled. Same here, 8 squared plus 15 squared did make 17 squared, so yes, it's right angled. Whereas here, 6 squared plus 12 squared did not make 13 squared, so no, it's not right angled. So that's the answers to the first part of the sheet. And to the second part, it's all about setting out the working. So this is not the full working, it's just what you should have demonstrated is, in this case, having worked out the missing edge here being 12 on the green triangle. So using Pythagoras, you work out AB is 12, and then you show that 9 squared plus 12 squared makes 15 squared, but you have to make the appropriate statements. Since AB squared plus BC squared equals AC squared by the converse of Pythagoras' theorem, the triangle is right angled. Now it's right angled at B because B is opposite the 15. Now similarly for the other questions, the missing edge here is 20. You're showing 12 squared plus 16 squared equals 20 squared. Now it's important to use Pythagoras on the green triangle and the converse on the red triangle. So in this one, the missing side AC is 25, and you need to show that 15 squared plus 20 squared equals 25 squared, but you need to set out the appropriate statements. So that's the converse of Pythagoras' theorem. The worksheet can be downloaded using the link, and while it's not the answers in part 2, it shows you what you should be looking for. Unlike all the other Pythagoras' theorem videos, there's a set of notes you can download from the link. There's the converse, and it covers previous videos. Hope you found the videos useful. Thank you.